talk about a case that happens so often in circuits, which is where you have amplifier case where you may have like maybe two different amplifiers, two different time constants, and particularly you have feedback around that particular structure. This is a structure that shows up in so many different places. So in a case where you might say, look, I have a first transfer function, a second transfer function, and a feedback where I'm taking the difference of the two. Maybe sort of taking a difference of something, you can imagine many ways this happens in circuits. And so if you were to say, well, how would I think about these kinds of structures? Well, you could think about one structure as being a high gain amplifier, and maybe also, but again, it has a first order pole because there's going to be some capacitance there. So you might imagine it being like a source or like a common source structure. You might get something that's like a source follower that also has a low gain, so a gain of say 1 or kappa. Some might look at this and go, wait, this gain should be kappa, and that would be correct, but we'll just keep it simple for the moment. And keep it at 1. And so then you look at this question and you go, well, now hold on a second. How does this all work when I connect these things together? And this is like one of the more common things, because often I'll want, say, a high gain amplifier to influence a low gain source. And you think, well, that's not too much of a problem. You just hook it together and you look at it. But it turns out the feedback of this gets rather interesting, because in a very simple sense, I can sort of write down, I get the combination of transfer functions. The output then is this sort of interesting combination of these elements, which, looking at this carefully and assuming that the gain is large, which of course we'll show the example it is, but typically you have that first gain to be, a significant number, that first term disappears, and so I basically just have the 1 plus a term in S plus a term in S squared. Okay. So now when I look at that, I think, well, that's kind of interesting. That gives me a very interesting transfer function to look at. It turns out I get a very interesting case, which is if I assume that the 1 tau is approximately a gain times the second tau, right? So in other words, somehow those time constants are split by pretty much the gain of the first amplifier. This actually simplifies, and you can see it here, that this will just turn out to be tau squared. This simplifies effectively to just being tau 2, because what you're going to have is this is now going to be a times tau 2, and I get a transfer function where it looks like I have a transfer function of a q equals 1, which is sort of typically what we're looking for. That sort of typical 45 degrees of phase margin, sort of optimal step response. And it's an interesting question how this plays out, because if I didn't do that, let's say I made the 2 taus equal, I don't get a q equals 1, I get a much, much higher sort of resonance in this circuit. And that may or may not be what I want, particularly if I'm making sort of it's something that is going to have a robust step response. That's probably not what I'm looking for. And so what's the implication of that? Well, if you look at H1, which is a high gain, maybe it's a gain of 100, and then it falls off as a first order response, right? Integrator response at this stage. Maybe you'd think 20 dB per decade response. And you can definitely see that there's a gain of 100 there. Well, if I plot this and I plot H2 as having now a gain of 100, or having a tau that's 100 out for a gain of 1, you would look at this and say, oh, okay, I can kind of see these two responses. They are quite separated apart. And this becomes quite a significant constraint for a number of different circuits, because either it means make something go faster, usually you need to gain 1, or or slow something down, and I have to be very careful of this. Well, if I do this, then I definitely get a nice q equals 1 types of frequency response over that range, and I can kind of see how everything lines up all the way through, particularly at the gain of 1 equal point, right? Gain of 1 there, there, and there. So again, this is probably a very reasonable response, and depending on your situation, you might be able to tweak it one way or the other. Again, there are times you want high resonance, and maybe if I'm looking for a high resonance system, I would do something different. But if I'm looking for a good stable structure, for example, if I'm looking at, say, like a current input sort of transimpedance amplifier, and this structure shows up in many places, For those who are familiar with the adaptive photoreceptor work by Tobi Delbruck, you'll see that this is sort of a core piece of the concept. But you'll see this show up again and again where I have maybe some sort of sensor, say some sort of typical currents. And I take this, and maybe this sort of circuit on its own is pretty good, but I'm going to use an amplifier in the feedback to do something, say, like fix this voltage node and maybe decrease the capacitance loading of that sensor or something equivalent. Well, in so doing, I've got this entire sort of stability question now that I've just addressed. And I have to think about that and how those things interplay. What gets more interesting in a circuit like this is time constant of H1 may be set, okay, but the time constant of H2 is not set because it's entirely dependent on what the input current is. And so for an imager, that can be orders of magnitude in size. So although you think that it might be safe at one bias point, you have to then think about how this plays over a whole range of currents and therefore a whole range of light levels. And this problem shows up again and again many places, which is why it's important to kind of talk about this kind of baseline problem and what happens when you start to add these two time constants together.